Good evening, everybody. My name is Cesar Torres. I'm presenting this on behalf of my collaborators, Tim Campbell, Neil Kumar, and Eric Paulos. This is work done out of UC Berkeley in the Electrical Engineering and Computer Sciences Department. Today I'm going to be talking to you about a project called HapticPrint, and this is our vision for really changing the landscape of 3D printing to move away from just form-first factors to really factor in the kind of haptic features that really define objects. And so this is one of these trends that we've been noticing in 3D printing, this move to try to create that final artifact, to go to make things stronger, smoother, higher resolution, to increase the diversity of materials in order to get a really high fidelity object. And so we see products like this in the market. This is Smooth On, it's an epoxy coating, and it's really trying to emulate these high-end manufacturing projects such as injection molding and remove that artifact that you see that comes from FDM fabrication processes. And so what we're seeing in communities such as Thingiverse is this really constrained aesthetic. Just like from these objects that were just randomly sampled from Thingiverse, you'll notice that they're all smooth, they're all rigid, they're all uniform, and they don't really convey anything past that. But we know that objects are not smooth, rigid, and uniform, and really this is limiting that design space. So with this project, we're asking this question of how can we add that same type of physical expressivity into the design of physical objects, things like patina, and multiple materials and form factors for the human body. Specifically, how do you even go about designing the feel of an object? In order to look into this question, we looked at the field of haptics, which according to ISO is divided into really two fields. Cutaneous touch, which is the mechanical simulation of the skin, and kinesthetics, the sensation of movement, force, and position with respect to an object. We also looked at a body of literature in psychophysics, particularly this seminal work by Lederman and Klatsky, where they identified 6 exploratory procedures that humans use in order to make sense of their world. And these are lateral motion, pressure, unsupported holding, contour following, static contact, and enclosure. And so if you look at the space of 3D design tools available today, really enclosure is the only type of exploratory procedure that is supported. And in order to limit the scope of this project, we looked particularly at passive components. So HapticPrint is a set of design tools to enable this type of haptic exploration in the design of physical artifacts. In a nutshell, we created this external design tool that specifically leverages haptics with cutaneous tactility, and an internal design tool that is focusing on kinesthetics. Now, many in this field are looking at ways of enhancing the expressivity of physical materials through 3D manufacturing. In particular, there's work that looks at making dynamic interfaces using things like pneumatics, as well as the new expanding body of work that's looking at multi-material printers, so creating and computing gradients and dithering between multiple materials in order to achieve new types of behaviors. And as well as work that looks at manipulating the internal structure of 3D prints in order to achieve things like balance. Our contribution to this field is three types of haptic features. In particular, texture design, which we accomplished using a 2.5D traditional graphics technique. Compliance design, which is achieved through a series of haptic infills that allow you to control compliance across several dimensions. And weight design, which allows us to shift the mass distributions of an object post hoc through injection. And all of this is accomplished through a consumer-grade 3D printer, single material. I'll first start by talking about texture. Specifically, how is texture used in physical design? As you may well know, It is a form of communicating actions to a user through affordances. It also aids in usability by allowing users to more finely control the turn, as well as its value as an assistive technology by imparting richer cues for the visually impaired or for operating this lens in the dark. And so we accomplish this by a technique known as UV mapping. This maps a 2D graphic around a mesh, and using the grayscale value, we're able to control one dimension. Through this, we parameterize a couple of designs. What you're seeing here is a height map for a bump. And we're able to control the feature size and feature gap of these features, feature gap and size, which are important for, these are one of the two dimensions that we've identified that can really generate a diversity of tactile feels, such as softness and abrasiveness. This is then converted into a tactile model. In this case, I've just mapped this, this image onto the top plane of this prism. And you can do things like manipulate the magnitude. And this is something that you might want to use for designing that doomsday button, this do not touch aesthetic, or you can go for something a little bit more subtler. In the end, we printed these, in order to evaluate the effectiveness of printing these tactile features using an FDM type process, we printed it on a set of primitive objects that represent all build directions on a printer. And I want you to in particular note that these are printed using a thermoplastic elastomer at 0.1 resolution. And so if you look at the feature size of these particular textures, you'll notice that this grain that is so much a trend to try to remove is actually obfuscated in this kind of alligator print. But again, we run into problems such at the top of that cone where the filament didn't have enough time to dry. But that can usually be mitigated by changing, by letting layers cool down. In this next set, I'll be talking about compliance. So compliance is usually used to convey the mechanics, how you actually move an object. So in the case of cardboard corrugation, it conveys that cardboard is an anisotropic material. It only bends in one direction. Whereas styrofoam also conveys this type of impressionability, right? And it's a much more playful interaction. In order to achieve this, we looked at controlling or designing a couple of new infills for 3D prints. So infill is usually just used as a support structure. It's used so that you don't have to print an object completely solid. But in this case, we leverage it with the thermoplastic elastomer in order to leverage different types of compliance. So you'll notice that this is the build direction here, and it's compliant along the X and Y, and less compliant along the Z. And this is also true if you apply pressure at diagonals. So using these types of infills, we're able to control the type of compliance. In order to characterize this, we built this jig that measures displacement as a function of force. And we calculate this K value from a series of tests. And what we found is that our linear models suggest that these can, in fact, be modeled as linear springs. And this means, given our knowledge of human pinching strength, so this usually varies between 50 and 100 newtons, we can characterize just exactly how much displacement will occur in millimeters based off of a light pinch, strong pinch, or that maximum, like you really want to hurt somebody pinch, through different infills, infill densities. Lastly, I want to talk a little bit about weight. So weight is actually one of these features that is well characterized in a physical design literature as playing an important role in conveying the trustworthiness of an object. So for those of you who have held a drill like that, or a drill like that, the the feel of one is completely different from the other, where on the right it's a little bit more trustworthy. And I want you to particularly note the position of these buttons on these drills, because weight is actually an important way of denoting surfaces of interaction. So, just going back here, these are particularly positioned where the hand might fall, and this is all really dictated by weight. And in the case of a remote control, the batteries are positioned at the bottom in order to act both as a cantilever when you're pressing buttons on the top, but also to indicate that the top is the surface that you're going to be interacting with. So in order to accomplish this, we developed this haptic pattern, and what this does is that it allows a couple of channels, so that after a object has been 3D printed, such as the case here, this is just a cross section filled with black sand for contrast. We can inject a material, and depending on its viscosity, it will fill this chamber. And so in this way, we can create things such as weighted bases or axes. We used a variety of materials for kind of seeing how we can explore the weight design, including dynamic materials such as ball bearings, or for like a rain stick effect, iron filings, and acrylic paint medium. But this technique also lends well to low-cost materials such as hot glue and sand. In order to achieve this, we modified Ultimaker's Cura engine, open source slicer called the Cura engine. And this is what the tool looks like here. The user, in this case, is able to specify the number of chambers that they'd like to create. And in this case, they can change where that partition occurs, and quite simply change the pattern of infill and density from this screen. And so this is roughly what this G-code produces: 2 chambers. There is a division between the chambers in order to contain liquids or other particles. And with this, I'd like to display some of the objects that we've been able to create with this. So here's an example of a file. And this is what a user might see in a CAD modeling program. When we applied the techniques that we developed with HapticPrint, we were looking at ways of conveying more tacit knowledge through these textures. So for those of you familiar with files, unfamiliar with files, files are only supposed to be used in the pull stroke. And so in order to convey that, we developed this sawtooth texture. And so that sawtooth is abrasive in one direction and smooth in the other. And so this conveys a really subtle tactile cue to haptic cue to the user of correct tool use. We also see a great value in mixing these different types of compliance in order to achieve additional functionality in the case of stamps. So here is a kind of showing you the difference between a material that was printed less compliant and more compliant, and it adheres better to the paper. And this, what you're seeing here, this is an ink stamp. This is an emboss stamp. Embossing is actually a great technique for achieving haptics on paper. It leaves a nice emboss on usually on cardstock, and you'll see those in greeting cards. Lastly, I wanted to share with you this vision of haptic print as aiding with tangible user interfaces. So in this simple setup, the printed artifact is used as a dielectric in a traditional CapTouch sensor. And so what this allows us to do is be able to be able to use 2 different types of thresholds to detect 2 different types of event, both a press and a touch. So in this graph here, you'll notice that as my finger approaches, it'll go down into this touch. And as I press this compliant button here, I'm able to also reliably detect press. And so with that, we looked at ways of how do we actually integrate this into practice, because as you might imagine, it's very difficult to even convey how things should feel in a virtual interface. So we created a set of referential palettes similar to the Pantone system, or as somebody put it, the kind of RGB of tactility. In this case, we ordered these based on feature size, gap size, and a smoothness index that's referential to the set of textures that we created. But this also assists in a very difficult problem within the product design community, and that it's very difficult to actually convey. There's a very limited language surrounding haptics. So with that being said, this work, of course, has limitations. For one, we did not conduct a formal psychophysics evaluation, and that is primarily because it's a very difficult problem in psychology to factor in all these different types of haptic features. You can't really evaluate one in isolation because each of them informs one another. And of course, we are manipulating the infill, and that also has an another purpose for acting as a support structure. So really, you can't do infills less than 10, 15%. And with that, we see great opportunities to explore static contact, this one last exploratory procedure, and looking at temporal patinas. So with that, I'd like to thank the reviewers for their really insightful comments that really developed this paper. And lastly, I'd like to dedicate this talk to my close friend and colleague, Tim Campbell, who was really one of the, really the inventive force behind this project. So with that, I'd like to open it open to any questions. Thank you.
Hi, MIT Media Lab, Ken Nakaraki. Nice talk. And I was thinking, I thought it's interesting when you are talking about fulfilling the inside with like some kind of dynamic material, like a magnetic something. Can I hear more detail about how you like manipulate them, and also like the application, how to use this dynamic material property?
Right. So in our case, we don't really look at the interactivity aspect within the infill, but it's something that we definitely see as valuable, you know, taking magnets to it and even being able to detect the internal structures or how things move around. But really what having this dynamic weight aids in conveying to users how objects should be used. So, you know, a rain stick is something, you know, that tells you that you can go from one mode to another, right? And so in this way, these artifacts can be used to create, you know, modal interfaces. So we're primarily looking at the physical design aspects, the passive features, but it definitely is something that we're looking to explore, especially in the case of, you know, these multi-material printers that can print conductive material. And leveraging capacitive touch using that.
I'm Chien Kim from University of Colorado, and I saw you use the UV map to cover all the surfaces of the 3D objects, and does that calculate automatically the normal for the spikes you created for the pattern?
Right, so in our particular implementation, we only provided UV maps for basic primitives, so these have already been created, and we created a UV mapping for radial. But programs such as ZBrush actually generate this UV map for arbitrary objects, so you can just use those points and those normals in order to get that correct UV mapping.
Hey, Daniel Ashbrook, Rochester Institute of Technology. I'm curious if you thought about modifying a 3D printer to be multi-material, but where one material is just sand or liquid or something that gives you that weight and frees up that cavity so that you can completely fill it.
Yes. Absolutely. Although I think that there's just something about still a user handling a physical material that aids with the overall process. Even, you know, injecting weight, you can change it at that moment and have a little bit more control on how things feel.
Thanks.
Yep.